We're welcome to lesson 3. So we moved on now to what's called the photoelectric effect. We're going to have 2 lessons on the photoelectric effect. Okay, so today's lesson will be about photoelectric effect in very general terms, and then tomorrow we'll be dealing with calculations involving photoelectric effect. So the good news is tomorrow we're back to calculations. Okay, so today no calculations. Right. The photoelectric effect, okay, caused a huge change in how we looked at light. Okay, because what happens with the photoelectric effect, similar to thermionic emission, so we understand that thermionic emission, if you add energy to the electrons that are kind of loose in a metal, the electrons might escape. Thermionic emission. The photoelectric effect, well, if you think about it, photo as in light, so the photoelectric effect is the same for light. So if you shine light energy onto a metal, electrons may escape. Now, the problem was that the amount of electrons that escape couldn't be explained using the wave model. Okay, so we have the wave model from Young-Slit's experiment and so on, but the photoelectric effect could not be explained in terms of the wave model. In fact, for example, in one situation, the wave model predicted that electrons would be emitted after 15 minutes of light shining on the metal, and in reality, it was less than 1,000 millionth of a second. Bit of a difference. Wave model not working for the photoelectric effect, so we have to improve the model. Back to proving the model. So the model was the photon model, and no better man than Albert Einstein who came up with this. And it was for this work that Albert Einstein got his Nobel Prize in 1921. Okay, on how the photoelectric effect can be explained. So pretty dramatic stuff is the way he operated. Okay, so let's go through what he said. First of all, he said, and this is the most important bit, he said that energy is made up of packets of energy, which we call photons. Just packets of energy, not waves, packets of energy called photons. So, okay, so energy consists of photons. Okay, that's step 1. That's number 1. Number 2, he said, and this is very important, that all of the energy from one photon is given to one electron. So all of energy of a photon is given to an electron. Now that is very important, okay, but it's also very useful for us because it makes the maths very easy. Okay, you're just zoning in on one photon, one electron, as we'll see. Okay, so they're the first 2 crucial points. Okay, so we want to look what happens then. Okay, so let's draw it. Okay, so we have our metal and we have our electrons, and the electrons can be released pretty easily, but they still require energy to be released. Okay, now I would suggest that you have page 1, your definitions open in front of you if you can. Okay, because we're going to be going through a lot of definitions here. Okay, so the first one is the energy needed to get the electron to escape is important. And we have a special name for that, and it's called the work function. It's a traditional name, but work and energy, remember, are the same. So the work function is the energy needed to completely remove the most loosely bound electron from the metal. Okay, and that definition is there, but it should make sense to you that we need it. And the symbol for it is that, okay, phi. So work function. Okay, that's the work function, right? That's the work function. Now, the second thing was that the energy of a photon of light, okay, was proportional to the frequency, proportional to the color of the light, and so on. As we've already looked at that when we were doing waves, that energy was dependent on frequency. So basically, Einstein was saying the energy of the photon is proportional to frequency, and the constant, since it's proportional, is h, which is called the Planck constant, named after the other guy who was heavily involved in this, by the name of Max Planck. Okay, tiny number. It's 0.0 followed by 34 zeros, 634, a tiny number. Okay, scientific notation, it doesn't look too bad, but try writing it out. Okay, it's a tiny number. So that's the energy of a photon. So light travels in photons, and that's the energy of the photon. Okay, we need to have that. Okay, the photon gives all of its energy to one electron. Okay, and the energy that electron needs to escape is called the work function. Okay, that's called the work function. All right, so I'll be clear on that, right? Now, what if there's enough energy? If the energy, let's say we'll talk simple numbers. let's say the energy of the photon was 12 and the work function was 10, right? Will it escape? It'll escape, okay, because it has the energy. Will it have energy left over? It will have energy left over. And when the electron escapes, the leftover energy will be kinetic energy, the kinetic energy of the electron. Okay, so let's go through that again because this is the crucial point, okay? And I'm going to write it down, okay? So the energy of the photon, that's the energy come in. We're only talking about one photon and one electron. It uses that energy, first of all, to escape, which is the work function. And then any energy left over is the kinetic energy. Okay, and that's it. Okay, right. Now, we'll write the mathematical equation that follows on that, okay, which you'll be familiar, you should, at this stage, you should better work it down to this with me. The energy of the photon we've said is HF, the work function we've said is phi, and the kinetic energy, you know, from mechanics way back in September, is a half mv squared. That's Einstein's photoelectric equation. That is what we'll be dealing with tomorrow in our calculations. Something to look forward to. Okay, so that's it. Now, that's not where it ends, okay? There's a little bit more going on, okay? Because if you think about it, right, what happens if the frequency of light is too small? So therefore the energy of the photon is too small. The work function, if it's less than the work function, no electrons are emitted, okay? So if the energy of the photon is less than the work function, no electrons emitted. If it's more than the work function, electrons are emitted. So we'll stick with that for the time being. In the same way, if it's, we have a frequency, okay, the work function is the energy. So if we take HF, there's a frequency that is related to the work function, and it's called the threshold frequency, which is the lowest frequency needed of light for the electron to escape. So you'll see your definitions, you have two definitions. Okay, the work function is the minimum energy required to completely remove the most loosely bound electron, and the threshold frequency F subscript 0 is the minimum frequency to blah 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 blah, exactly the same thing. So the two definitions are almost identical. So work function and frequency. So E is equal to HF, look at it, and if E is the work function, F is F0, the threshold frequency. Okay, so that's the other one. So below the work function or below the threshold frequency, if the energy of the photon is less than the work function, or the frequency of the light which contains the photons is less than the threshold frequency, no electrons can escape. If it's above it, electrons can escape. Now we'll come back to that tomorrow. That's enough for today. We're going to go back to that tomorrow, and we're going to, there's a bit more going on. Okay, what happens if you make if you're sending in loads of low energy photons? Okay, now you looked at the you saw this already with our new friend Jim and the beach. Okay, so you want to think about that. Okay, think about that, and we'll come back to that tomorrow. Okay, but before that, right, I want to look at two more things. Okay, we're going to look very briefly at two more things, and again, one of them you've seen with Jim already, and you're going to see in the video that you're going to watch after this as well, okay, which is the experiment to demonstrate the photoelectric effect, but we'll just run through that on the board, and then we're going to look at a thing called a photocell very briefly. Okay, so, and then we're done. Right. So, the experiment on the photoelectric effect. Okay, so let's have a look. Okay, so what we had is a gold leaf electroscope. Okay, and you saw it in action in the video. Okay, so effectively, all it is a metal cap. Okay, metal down here, and you have two gold leaves. Now the gold leaves, because the gold leaves are very, very light and they're easy to move. If these have the same charge, okay, if these are the same charge, they repel. Okay, and that's what you saw in the video, and you'll see in the next video as well. Okay, on top of it, we put in a clean zinc plate, as we saw, a clean zinc plate. So, and we charge this negatively by induction. Now the charge by induction, not relevant to this section. We'll be doing that in electricity next year. Okay. Now, so we have a negatively charged gold leaf electroscope, and we have a clean zinc plate on top. Okay, and we shine visible light on it, and nothing happens. Okay, the electrons stay where they are. It stays, the two gold leaves stay repelled. Okay, but if we shine ultraviolet light, now ultraviolet light, remember, has a greater frequency, therefore it has a greater energy of photons. Okay, and it turns out that ultraviolet light has a work function that's greater than, has an energy of photons that are greater than the work function of zinc, and a threshold frequency that is greater than a frequency that is greater than the threshold frequency of zinc. In other words, electrons will escape and they'll have kinetic energy and off they'll go. Now, if electrons escape, you're going to lose negative charge on the gold leaves. So what's going to happen to the gold leaves, as you saw? They collapse. Okay, they collapse. And the term we use is collapse to be dramatic. Okay, they collapse. Don't fall down, they collapse. Okay, so that's that experiment. Okay, so you've seen it with Jim, and you're going to see it repeated now in a very short video. You're going to look at it in a minute. Okay, lovely experiment, and you'll be doing this experiment yourselves in when we get back to coursework. Okay, final one. Okay, is the photocell. Okay, so the photocell, and just a little tip on this as well. Okay, photocell. We're back to the evacuated glass tube. Okay, so we have a glass tube. Okay, and in this case we have a cathode. Okay, but the cathode is what we say semi-cylindrical, very badly drawn there. Okay, semi-cylindrical cathode, and we have a wire anode. Okay, now the reason of this, and so there's a vacuum in here again, so the electrons that escape will not be affected. Okay, and we need to connect these together. Okay, so if we have a power supply here, okay, sorry, the wrong way around, because that's the cathode, so minus, and let's say put in a microammeter here to measure current. Right, okay, so this is the cathode, and this is the anode. Okay, so if light of suitable frequency shines on it, okay, the wire anode doesn't block out the light, so the light will get to the cathode. Okay, photoelectric effect will occur, the electrons will be emitted. If this is designed correctly, so that this is if you think in 2 dimensions, a circle, and the anode will be the center of the circle, so if the electrons are emitted at right angles, they'll all hit the anode. They'll be attracted to the anode anyhow because it's positively charged, and the electrons have a negative charge. So therefore, electrons will travel from here to here, and current will flow through the gap. A little bit like cathode ray tubes. Okay, it's like a cathode ray tube, but a special version. So these are the photocells that as we walk up to a door and the door opens. Okay, these are the photocells that detect the absence of light as you walk and break a beam. So that's your photocell. Okay, so let's just recap on the 3 things that we're looking at so far. Okay, today. Okay, you understand the photoelectric effect experiment that you'll be doing yourselves later. Okay, the photocell is an application. Okay, and then crucially, okay, let's go through them again. Okay, Einstein says, so it must be true. Okay, number 1, light travels in photons, energy is equal to hf. Number 2, and this is crucial, all of the energy of 1 photon is given to 1 electron. And number 3, at the moment, okay, the energy of the photon equals the work function plus the kinetic energy. So in other words, once you've got the electron to escape, you've used the work function energy, and any energy left over is kinetic energy, and off you go. Okay. Below the work function and below the threshold frequency, no electrons emitted. Above the work function and above the threshold frequency, electrons are emitted. Now, there's a lot in that. Okay, hopefully, while listening to Jim in the early movie, watching this, thinking about it, okay, I want you to go over this. I'm not going to give you much to do other than trying to figure this out in your head. Have that comfortable, and then tomorrow we take it one step further, and then we do the calculations. Calculations are fine, as you'll see. Okay. And before, what I forgot to say is that Einstein's photoelectric equation is just a statement of principal conservation of energy. The energy before of the photon is equal to the energy after, the work function to get the electrons off, and the kinetic energy. Energy before equals energy after. It's all about energy. Thank you very much. We'll talk to you tomorrow for calculations. Bye bye.